This conference will now be recorded.
So last time we stopped at gradient descent. Do you have any question for it about it? So okay, then let's move. Backpropagation. So we start with a simple explanation about backpropagation. So backpropagation is how are we going to tell us how are we going to update the weights of my network. If you remember last time, like we saw that each neuron has a weight, has some weights. Do you agree with me, guys?
Yes. Yep.
Yeah, and we want, the goal is to update these weights to minimize the error. That's the goal. We have an error that we compute at the output. Each output neuron is computing something. And then we have an error that we compute at the end. And we update the different weights. So the output will become smaller. And we keep doing it till like we cannot update anymore. We cannot improve the error anymore. So that is what we discussed last time. And we saw that we do it with gradient descent. We have the loss function that we are trying to optimize to find the minimum. Once we find this weights, then we have our network and we can start running the predictions. So backpropagation, this is a simple explanation. We are going to explain it in two ways. The simple explanation is more intuitive, and then we will go to a more mathematical explanation, which is mainly the real explanation. So what we do in backpropagation, we loop around our data set. So we have some data set and we loop around it. We check if the output of the network is correct. If it is not, we update the weight so it can become more correct. That is what I just said. So how do we assess the blame for each neuron? We have multiple neurons, and we are going to see which neuron is more responsible for this error. That's the goal. So the neuron that is more responsible for the error will receive obviously more change. It's trivial. Do you agree with me? The neuron that will be responsible for more errors is going to receive more change. We are going to update it more than the others. Its weight will receive more updates. So this is the intuition. So this is the neural network, an example. A are the inputs, A1. Then this is the outputs of A2. So Z and Zs, the Zs are the outputs, the final outputs. A are what is computed by a neuron, and the Z is the output after applying the activation function, like the sigmoid last time that you saw like this. Just to you remember. Well, the sigmoid is the opposite, like this. So we have this kind of things here. So we have A's that are computed, and then Z is when we apply the sigmoid. So we have multiple A's and Z's, multiple inputs and outputs. And then when we compute, guys, the errors here, we can know, for example, if we have a high error here, this output is multiplied by some weights. So we have outputs here that will be inputs to this neuron. For this neuron, the outputs of this neuron, or the outputs of all of these neurons, will be inputs to this neuron. When we compute and we see that there is a high error here, this neuron, if we take this neuron, only this and this group, this neuron is computing what? This input, or this output from here, multiplied by some weights that is in this neuron. Some W's. It has multiple W's. It has actually 5 W's. This neuron has 5 W's. So we multiply one W by this, plus another W by this, plus etc. Then we apply the sigmoid function or an activation function, and we get our output here. So when we find an error, we have to see which one to blame. Is this the W's? Is it the W's? W1 till W5? Or these outputs, or these inputs to this? We can these outputs from this neuron, or which are the input to this neuron. So which one is to be blamed most? This is the goal. And the one that is to blame most is going to receive more change. We need to update it more.
Probably the weight.
Exactly. When the weight is multiplied by this, so the weight is telling me which one is influencing more this output. So the neuron here that is receiving a high weight should receive more update because it's not doing well. It's like having a high weight that is multiplied by it. Its output is multiplied by, for example, let's say W1 is a high weight. It's a very big weight. Then, and the other W's are very small. So this one is contributing to this output more than the others. What should happen then? Then it will receive more blame. You have a high voice and we are not doing well. So we need to blame you a bit more. And then we modify it more. It will receive more blame. This weights also will receive some blames, not just the outputs. These weights also, when they are high, they will receive more blames as well. So the highest things will receive more blames, the smallest things will receive less blames. This is like an intuitive explanation of backpropagation. Are you happy so far, guys?
Yes.
Great. All of you?
Yes.
So no, okay, perfect.
Can you repeat?
No problem. No problem. So we have this neural network. It's computing some outputs. So in each output, we are going to see the error. How much error are we making?
Okay.
And of course, we are going to blame the one that is more responsible for this error.
Yes. Yeah.
So we're having this output. We are going to blame the one that is more responsible. Is this one? So this neuron is just computing a sum of W's, which is its weight, multiplied by these inputs, which are the outputs of the previous layer. Let's call it Z's. Zi. So this neuron is computing this. So and we have an error here that we have computed. So the ones that are more responsible, the one that is more responsible, is going to be modified more.
Yes.
Which is normal. You modify the one that is more responsible to this error. The ones that is not responsible much, we're not going to be modified more. So we look at its weight, for example. We have W1, W2. So the one that has a high weight is probably having more say in this error. Yes or no?
Yeah.
Because it's multiplied by a high weight. So this neuron,
Yes.
Yeah, this output here, if its weight is high, it means it's contributing a lot more than the others. So we blame it more, which is normal, and we ask it to, we change it more. We change its output more. Same for W, of course. W also will be modified more because they are both responsible for this high error. So this is like the intuition. And we do the same thing because the output here depends on the previous layer. So once we blame it, say we tell it this neuron is responsible for 20% of the error. So this 20% again is going to be distributed into the neurons before it because this neuron depends on this and the inputs. So it's going to be distributed like a bit. We take a small chunk, give it here, another, and based on the weights that are in here. Another chunk, we give it in here, etc. And we modify it based on the amount of blame that it is receiving. And that way, we end up updating the whole weights of the neural network. Are you happy, Yusuf, so far?
Yes, yes, clear. Yeah.
Yeah, we are just distributing the weight. It's like a cake. Well, it's an error. Normally, it's something negative. But let's see it from like a cake, and the one that is contributing more to the cake will receive a bigger slice. That's it. Well, that's what I was explaining. And the blame is propagated till the end. And we update everything. Now, let's look at a more mathematical explanation. What we had just seen now is something that is more intuitive in terms of explanation. But this is more of a mathematical explanation. So, in reality, backpropagation is a way to compute the gradients, and a fast way. There are multiple ways of computing the gradients, not just one way. Like I said, the gradient is the slope. For example, for this function, the gradient in here is the slope. It's something that is like that. For this point in here, the gradient is pointing towards this direction. It's the slope of the point. So there are a few ways to compute this gradient. We have the numerical way, and we have the analytical way. If you remember in high school, you used to compute the derivative of functions. I hope all of you remember that.
Yes, yes, yeah.
We used to compute the derivative of functions. And how did you do it? Function like this, for example, fx equal, I don't know, cos of 1 plus x divided by x squared plus sine of x squared divided by x plus 1, something like that. So what did you do? You took a pen and a paper, and you start playing with it.
We calculate derivative.
Derivative, because here we have a plus, you do the derivative for this part, plus this part, and you look at the derivative at cosine, which is it's the derivative of the cosine multiplied by the derivative of what is inside, etc. You do it like with a pen and paper, which is the gradient actually. It's the same thing as the gradient. The gradient is the derivative. It's computed via the derivative. However, if you have a network that is not large, for example, that one, so it's mainly a multiplication and additions and the sigmoid function, or if you are using the sigmoid activation function, because this one is inputs multiplied by some weights plus other inputs multiplied by some weights. It's a lot of additions and multiplications. This neural network can be converted into a function, a written function, and an analytical function. Yes or no? Tell me, guys. We can convert it to a function, to a written function. Fx equals something like this inputs multiplied by the weights plus this input, etc., until we do the whole computations. Do you agree with me in this point? This neural network,
Yes.
we can convert it into a function because it's just a bunch of multiplications, additions, and activation functions.
Yeah.
That's all. It's a neural network is just a function, like written in this form.
Multiple variable function, isn't it?
Sorry?
Is it multiple? Let's say
multivariate function, indeed. Multivariate function. So we have what we call the numerical gradient. This is a very simple way of computing the gradient. what you do, for example, if you want to compute the gradient in X, you look at a point close to it. For example, this one. You look at a point close to it. This is an approximation of the gradient, and you see like the difference. So it's X, and here the second point is X plus H. H is a small number. So we do this, which is this length, Fx plus H, this, minus Fx, which is this length, divided by H, which is this length. So we compute this angle. So it is this divided by this. And it is a tangent. The sine divided by cosine, it is a tangent. And this is the slope, actually. This is the value of the slope. Well, if H is too big, we are going to make it, going to have a high error. For example, we go here. If H was here, the slope will be different, will be here. The real slope is like this. So this one is close to it. It's very close to it. So we call this way the numerical gradient. We choose a point very close to X, and we draw the triangle, and we divide this length by this length, and we get the slope. This is the numerical gradient. Happy so far? Are you happy, guys, with what is the numerical gradient? You can see it.
Yeah.
Great. So it works well, but it is just an approximation, and it is general. You don't even need to know the derivative of a function if you want to use this. You don't need it. It can suffer from the lack of precision, and if the gradient is very small, for example, something like this, and we go here. We go here, and we, for example, the point that we are going to find is, for example, here. The gradient here should be like this, but here, because we are close to a minimum, if we take this point, the gradient will be almost flat when we compute it this way. So it can suffer from this kind of precision. And when we are close to a minimum, this what we call the numerical gradient tend to become almost zero or zero. And if it is zero, we don't know to what direction we should go. For example, here, if we are here, if it is like a zero, the gradient can't find something. We don't know that we should go towards this direction to find the minimum, because the lack of precision doesn't allow us to go that far, to go into this direction. So it has some problems. So this is what I was talking about, a gradient with a pen and paper. You take a pen and you derivate, you compute the derivative. The loss function is the derivative of the loss function. The loss function is just, we can see here, a sum and multiplications and some logs. Here you have the input of the network, which is also a sum and multiplications. And activation functions. Activation functions are just 1 divided by 1 minus exponential x. So it's just a bunch of like a formula, a very big formula. With this kind, if you want to now compute the gradient by a pen and paper, if we have a network that is that big, how long will it? This is a small one, but let's say we have 1,000 neurons with like 1,000 neurons, let's say. So each thing in here will have like 1,000 parameters here, multiplications, additions, etc., and they can even repeat in the different in here and there. So how long will it take you to compute the derivative of this, a multivariate derivative? Tell me, guys, how long will it take you? How long will it take you, guys?
Too long.
Very, very long.
Yeah.
And maybe a whole notebook. Maybe you need a whole notebook, like 100 pages to compute a derivative that is that big. So we avoid doing this, and we use backpropagation. In backpropagation, we use what we call the chain rule. This probably like something that you studied before, but maybe you forgot it. The derivative, this means that's just the derivative of f, like a combined function, two combined functions, f of g of x equals the derivative of f with respect to g. So g becomes the variable. This will be like one variable multiplied by the derivative, the local derivative of g with regard to x. Can you see it? Like the derivative, this derivative equals the derivative of f with respect to g. It's like g becomes the variables. It's no longer a function. You look at it like a variable, like x. And then we multiply it by the derivative of g, this one, with respect to x. Sorry. Okay. An example. This is like high school calculus. Very simple. So if you want to find the derivative of f, if f equals this, 3x squared plus 5x minus 2 to 8. So how do we compute it this way? We can compute it the normal way, but this way it's much faster. We can do it very fast. So we take this. So we make gx as this, and f of g is this. Let's call gx y just to simplify it. So f of y equals this, equals 8y7. So the derivative of f of this of y, because this will become one variable, which is my g, its derivative will be 8. It goes down, and we reduce the power by 1. You remember this? It's like this one
Yes.
becomes one variable. We call this y. And then what we do, we can compute this. So this is this, and then we compute this with the derivative of g with respect to x. And this is it. This is very simple to compute. 2 we go here, etc. So we get this. So the derivative of this is this, 6x plus 5. And the derivative of this is this. We replace y by its normal value, this one, and we get this. And we compute the derivative. So it's a much faster, it's a faster way of computing the derivative, but the speed is for another reason that we are going to discuss. So it's a very fast way to compute the derivative instead of like multiplying this 8 times. We did this, and we were able to compute the derivative that so fast. If we had to compute it 8 times, it would be very long, like to compute and then to derivate. But this way, with the chain rule, it is much faster. Some of you probably remember this way of computing the derivative. Okay, guys. So now let's see more about backpropagation. So this is a simple example for backpropagation. This is a computation graph. So we have 3 variables. This is not a neural network, but just to make it something very simple. We need something that is quite simple. So we have 3 variables. We do the sum, and we multiply them by z. So this network is computing, it's not a neural network, it's just a simple network. It's computing x plus y multiplied by z. That's all what we are doing. And we want to compute all the derivatives with respect to x, y, and z by using the chain rule. We can compute it normally, what we call a pen and paper method. But we want to use the chain rule. So what we do in the chain rule, we transform this as G. So this becomes G. And F of G equals what? G multiplied by Z. So F of G equals G multiplied by Z. G is a function, and G equals what? G has two variables, x, y.
X plus Y.
Exactly, x plus y.
X plus Y.
That's what it is. So to use the chain rule to compute the different gradients, what we do, we compute the derivative of f with respect to g, which is what? It is z.
Z.
Yes, it is z. So we got z here. And when we compute the derivative of x, well, to compute the derivative of z, we just, it becomes the variable, and this becomes a constant. This is like the partial derivatives. The derivative of z is g, which is x plus y, which is, in this case, minus 2 plus 5. But here, the derivative of g is z, and the derivative of x is what? Is, like the chain rule said, the derivative of this multiplied by the derivative of g. G equals what? The derivative of g with respect to x, which is what?
1.
1, exactly. So this will become 1. And what we do, we multiply them. So this is the derivative of x. And for y, what we do? It's again z multiplied by, what is the derivative of, exactly, it's the same 1.
Yeah.
What happened here, guys? The derivative of z is used by these two, and we computed it only once. This is the gain. This is the main gain. The derivative of z, we computed it only once, and it was used by both. If you had to do the pen and paper derivative, we just forgot this z. We go individually for x, for y, and z. But here, we took advantage of intermediary computations, and this z was used. We get the value for z. We know the z it's minus 4, and we computed it only once, and it just propagates to x and y. And with neural networks, it's not just one propagation. You have seen that it is like a lot of propagations. We can have here like easily 1,000 neurons, and one neuron can propagate to all of them. And it has a huge saving in terms of time, in terms of computation. So guys, backpropagation is simply a quick way to compute the gradients. A mathematical guy will say for him, it doesn't mean a lot for a mathematical guy, because the derivative, computing it via the backpropagation or by a pen and paper, by any mean, it doesn't make it a lot. It's not a big difference. But from a computational point of view, it's a huge saving of time. So this is simply what is backpropagation. So this is the chain rule for y and the chain rule for x, and to compute them via backpropagation. So can we then now apply this chain rule to neural networks? Do they have like the same structure? Can we apply it to them?
It is more complicated, but
but we need to be correct. Can we still use it, or it will be incorrect? Do we have the same? We have the same intermediary functions, etc. For example, here we have a neural network. Do we have like the equivalent of G and etc. F and G, etc. Do we have something like that where we can compute the intermediate gradient for the neuron and multiply it by like the derivative of something that is coming before. Can we apply it? Like, is it correct to apply it?
It looks like it's not.
No, that is no problem. It's still, we are still in a computational graph.
Yes.
Yeah, it's still a computational graph. I haven't here this graph. It's still a computational graph, and it's a multiplication. It's like this. This is G, a function G. And if we like isolate only this two, so this becomes our G, and the derivative of these weights that are coming from here is can be computed by computing this function as a G. And same goes here. We have other weights. So we have the different weights. We have this gradient that's propagated here. And you can compute them still via backpropagation. It's like just a more complex graph. This one is a simple graph where we can use backpropagation. This one is a more complex one, but it still has the same structure. We have a function that is like this is this G. This G is a function of all of this because it multiplies their outputs by some weights. And this one is also a function of all of this. Let's call it J0. Is a function of all of this. Well, but this one is a simple function. So each output is going to another G. Same for here. This one, let's call it G1. It's also a function of all of this. But this one will be the general output will be the F, the last output. It's our F. And because it's a G of 0, and it goes, and this one will go inside F, it's exactly the same as what we had before. It's just more complex. And backpropagation will still work as intended. Do you agree with me, guys?
Yeah, it'll be all right.
So backpropagation will work perfectly. Well, it is not perfect, but it will work the same way as it worked here. A neural network is still a computational graph. So the goal here with backpropagation is to optimize the number of computations, and we compute the derivative of G only once. That's the goal, and use it for the layers that use it, which are the layers that comes before. In here, the gain, we compute the H or the G, sorry, here, and to compute the derivatives of this neurons, we just multiply them. We have our G, and we multiply them by the derivative of G, and we compute it only once. We call this, we can call it like a dynamic programming paradigm, where to compute something in here, we store something that we computed before, and we reuse it instead of computing the whole thing again. It's a form of dynamic programming. It's like we just reuse what we computed here before. Are you happy so far, guys?
Yeah.
Amel, are you happy? Yusuf?
Yes, yeah, I think
No,
so.
no, I'm not happy.
So you should tell me. Don't like be shy. Well, what shall I?
Just carry on for the time. Then I'll
No, that's fine.
do it
That's fine.
again.
Tell me what you want to like. Are you? Did you understand this part?
No, to be honest.
That's the problem.
Yeah.
So let's repeat it. Let's repeat the backpropagation, how it works. So as I said, we want to compute the derivatives for x, for y, and for z. We have 3 variables. Do you like follow the problem, Yusuf?
Yeah. Okay. Yeah.
The derivatives with respect to x, y, and z. This is a simple function. Very simple function represented into a graph, like a neural network is a more complex function that is represented by a graph. This one is a simpler one. We are computing what? X plus Y multiplied by Z. This is what we are computing. Fx, Y, Z.
Yeah.
So this is what we are computing this. We want the derivative of f with respect first to x, to y, and to z. Well, how we do it? We can do the regular derivatives. The derivative of f with respect to x equals what? This is a constant. This becomes a constant. So it is z. Derivative of f with respect to x is z equals z. Because z is multiplied by x. This is a constant. It becomes 0. Z multiplied by x, the derivative of xz becomes z. We can do that. But we want to use the chain rule. Like the rule that we have seen before. F of g of xy. This is z. So this one equals, let's call it g equals gxy equals gxy equals. So to use the chain rule, we use this. It equals what? To make it an intermediary function. We want this to be an intermediary function. It equals then x plus y, 5. It equals x plus 5, plus y, sorry. So we make this g. And because f of g, we have like a combination of two functions, we can use the chain rule. The derivative of this equals the derivative of g of f with respect to g. Let's solve this. F with respect to g multiplied by the derivative of g with respect to x. This is, so we use this formula. It's like we simplify the derivative. We don't compute the derivative at once, all at once. We use the derivative of this and we multiply it by the derivative of this. It's a bit of a mess. Let me do it again. So we use the derivative of g. We have to find g because we want to make a function that is complex, like in here. Are you following me, Yusuf?
Yes, yes.
Like let's take this example because it's more analytical. So we want to compute the derivative of this function. What do? We transform this as a g to make it like a combination of two functions. F of j of x. If we make it a combination of two functions, then we can use the chain rule. The chain rule becomes, we do the derivative, f becomes gx power 8, and gx is this. We have a combination, so f becomes equal to this. Then what we do the derivative of f first with respect to g. So this becomes a variable. You can call it y, and we do the derivative. Its derivative is this. We make 8 here, and this becomes 7.
7, yes.
Yeah. And we multiply it by the derivative of what is inside now. Because we took this as one variable, it is not really a one variable. It's a more complex one. So we have to, the chain rule says if it is a complex one, take it first as a simple variable, and you multiply it, its derivative, by this. Derivative of this with respect to x, which is this. So this is g, and this is its derivative. So we multiply this one. This one is 8yz, 8y to the power of z, and we multiply it by this. And we are done using the chain rule. Yeah, this is the total derivative. Using the chain rule.
Yes. This is clear, yeah.
This is clear, perfect. So that's all what we are using here. When we have, it happens that when we have a graph like this, a computational graph, we can, every node can becomes an intermediary function. Because this node is taking this input, the output of this node, as its input. So it's a function of this function. This function is more complex. It takes the output of another function.
Yes.
Which means we can make it, a computational graph can become something like this. Something more complex. And we can use the chain rule for it. The chain rule, we take this as a variable. We do the derivative of it with the derivative of this with respect to this. So we compute it. In this case, it became like we did z. We compute the derivative, and we multiply it by the derivative of this. Instead of computing the derivative of x by going till the end, we compute this intermediary value, and we multiply by the derivative of this with respect to x. So this value will be computed only once. Its derivative will be computed only once, and we use it for everything that is coming before. Are you happy, Yusuf?
Yes, yeah, it's more clear now.
Perfect. And then we do this. So a neural network is also a computational graph. And we do the same thing with it. We use the chain rule to compute the intermediate derivative that is in here. Here, we have multiple ones. And once we compute it, we use it to multiply it by the local derivative that is coming from here. And because we computed it only once, the derivative that for this node, the derivatives for these nodes are just going to be multiplied. We multiply the local derivative that we used by what we found here. So what we found here, the derivative is going to be used multiple times. So we don't need to recompute all the things to do this derivative. We compute the local derivative for this g function, if we can call it that way, and we multiply it to find the rest of the derivatives for the other weights. And we can gain time doing this. Are you happy, Yusuf? It's just a generalization of what we saw before.
Yes, yeah. And this is applies in each layer, yes?
Each layer depends on the other layer. And we can have tons of layers. We do the same thing. We do the local derivative and we backpropagate it to compute the derivative of the nodes, of the weights of the nodes that comes before it, until we reach the end.
Okay.
This way, we just are saving a lot of time computing the derivatives. This is the mathematical explanation. We have seen like a more intuitive explanation where we share the blames, but here we are sharing more. We are computing the derivatives, the direction of the blame, if you prefer, the direction that will reduce the blame. Okay, guys. Now, a problem that can occur with these derivatives. Imagine if our weights are very small. We have here some values that are multiplied. So imagine if our weights are very small, like in here. So if z was very small, so the derivative of I don't know if I got them in here. If I computed them. So we said that this is z, and this is what? This derivative is z. Is the derivative of this node, and the derivative of this is what? It's still z, because we have just we don't have a constant here or so. But imagine in here, what we are doing is what we are multiplying the derivatives, the local derivatives. We are multiplying to use the chain rule. We are multiplying it by the derivative of g by the derivative of the variables x, etc., etc. We are doing a multiplication, guys. I should have added a clear slide for this. We are multiplying, like we said here. Just to see this, we are doing a multiplication of this by this. And if we have multiple layers, we keep multiplying, because each multiplication will give me like the gradient of one particular weight. And the more we go backward, like that, the more we go backward, the more we multiply. Do you agree with me, guys? So this one, the gradient of this for this node, the gradients here are a multiplication of the derivative of this and the local derivative. If we had multiple layers, we do the same. So the gradient will propagate here. To find this one, we'll just multiply this one by the local gradient, local derivative, and we keep doing it. Do you agree with me so far?
Yeah.
Great.
Yes,
Amal,
okay,
Yusuf, guys, yeah, we just multiply. So if the values are so small, are very small, what will happen? Small means they are almost like 0 point something. If we keep multiplying values that are not small, what will happen to them?
We just increase the complexity of the system. So basically,
yeah, but what will happen to these values? They will become even smaller.
Yeah, become smaller.
They keep becoming smaller if they are all, for example, just compute like 0.5 to the power of 100. So it will become like a value that
They
is,
will be near zero.
Exactly. They will go near zero. And of course, our machines are limited. They can't represent 0.001 to infinity. There is a limit. Generally, we use 32 bits floats. They are limited to how much they can represent. At some point, they will just become zero in that case. At some point, they will become zero. Yes or no?
Yeah, then
yes.
then the neuron disappear.
Exactly, which means that the weights of the first layers, the gradients there will just disappear and they won't be updated. This is a real problem, a major problem. The weights, if we have a lot of layers, say 100 layer, well, it happens. It can have. There are models with 100 layers. If we do that, the weights are very small than the values. The first layers will not receive any update because we don't have enough precision for them. The value just became zero. We lost the precision. We call this problem, you're going to find it a lot. Can you tell me how we call this problem? It's a famous problem. It's a very famous problem in deep learning. It's called the vanishing gradient. It is called the vanishing gradient. This is the vanishing gradient. And there is another problem similar to it, which is the opposite. Imagine if they are big. We have big weights here and big values. And we are multiplying their gradients. Their gradients are high, say 100. And we have 100 layers. So this will become 100 to the power of 100. Not many machines can represent this. 100 to the power of 100. What will happen in that case? Tell me, guys, what will happen? Our 32 bits numbers are still limited. They can't represent infinity. So it will just explode. The number will not be represented. We will have sometimes some random numbers, or so we lose the real gradient. And this is the opposite effect of the vanishing gradient. This is called
problem of memory explosion.
Bits can't represent such a big number. It has its limits. It can't represent like very high numbers. Well, this I don't know if this can be represented or not by 32 bits, but there is always a limit. So, and this, if there is a limit, we can't keep multiplying until we can't represent it. We will end up with some random numbers, and we call this the exploding gradient. The exploding gradient effect. So it is going to receive a crazy gradient that is not correct, especially for the top layers, for the first layers. For this, we have so this is two major problems: the vanishing gradient and the exploding gradient. To avoid these problems, you have to normalize your data. Avoid having, like, for example, if you are measuring something, avoid having like very, very high data or like inputs that are amplitude or very small ones, and have a good strategy for weights initialization. You shouldn't like initialize your weights in a random manner that can create some problems. You have to have a good strategy. Let's see how we can initialize our weights. Do you want to pause, guys, or we can continue?
Okay, let's take break for. I want to pray Maghrib.
Okay, that's good. Okay.
Yeah.
So let's
5
have
minutes.
10 minutes. 10 minutes is fine.
Yeah,
Yeah, that's
good.
fine. Yeah.
Yes, thank you.
See you in 10 minutes.
This conference will now be recorded.
So this, as you could see, initialization and normalization, I mean of the weights, and normalization of the data is very important. Is to avoid making them too big or too small. So what do you think? Can we use to initialize our weights? Can we use zero initialization, just to put them all to zero and it's done? What do you think? Can we, like here, to have this graph and initialize them all to zero, all the weights to zero, and let backpropagation work?
No,
Would
it
it be-
cannot, because zero is like we don't have any sort of function if we use zero.
Okay, let's put ones everywhere. Would it be okay? And let backpropagation like
Absorbing.
sorry, what? If we put ones everywhere or in all the weights, would it be acceptable to start that way and let the gradient descent and the backpropagation do their job to optimize the different values?
I think so. That will be kind of works.
It's a quick solution, but there is a drawback here. Why? If we put them all at one,
We have done nothing here. Yeah.
Sorry?
I mean, if you do ones, then you change nothing.
You still change. No, you are going to change because the weights are one, and we compute the errors here, and the gradient will backpropagate, and we start changing things. We are going to get change based on the gradient.
But I think it takes, let's say, more time to adjust the numbers.
Possibly it takes more time, or maybe forever. The main problem, though, is when we use all, we initialize them all at the same value, what will happen? You can see that this output will be multiplied by the same weight. Same here. Same here. So when we start to distribute the blame, what will happen? They will receive all the same share. Yes or no?
Yeah.
They will all receive the same share of the blame, which means they will all converge to the same values. They will all be updated similarly. It's like we would have one neuron duplicated into multiple neurons. So we will not have this specialization. Normally, each neuron should be specialized in doing something, like we saw last time in the example of the XOR. So we had a NAND neuron, an OR neuron, etc. So neurons should be like specialized in doing things that are different and not the same things. But if we initialize things to like all the ways to be the same, the blames will be the same because they share this, they contribute equally, and every neuron will be the same as the other. And this is a real problem. We can end up like stuck on the learning. So what can we do? We can do what we call symmetry breaking. Symmetry breaking, we generally initialize the weights randomly with small values in the interval, in a small interval, without going too small, like 0.000, etc., and without going too big. Generally, this interval is smaller than 1. This value is smaller than 1. It's like minus 0.1, minus plus 0.1, this kind of things. And we have to watch out for the vanishing gradient if they are too small. This is not the best solution. We are going to revisit how we initialize these weights later. But this is like the basic idea, to have weights randomly initialized to avoid the symmetry. They should be different, and put small values. We have what we call calibrating the variance, where we try to have a fixed variance per neuron, or we can use even a more advanced method that we are going to explore later, which is what is called batch normalization. So I want also to visit some activation functions, because a neural network, if we don't use activation functions, it would still...
Reda, sorry. Just a quick question. In the previous slide, does that mean that we have a limit for the exploding gradient, but not a limit for the vanishing gradient?
No, we still have to avoid the vanishing gradient. We shouldn't go so small. We shouldn't go very small.
But we don't have a limit, do we? We can't set a limit for vanishing gradient.
Normally the function, the random generator will do that. It will not go like so small. We want to go to 0.00, etc. It will go to something like that is a region not very small and within this interval.
Oh, okay. Thank you.
That's what we do, because they are both equally dangerous, vanishing gradient or exploding gradient. Okay, and then we have the activation functions. Normally, in neural networks like this one, if we don't use activation functions, we will just have like combinations of linear functions, multiplications, and we just keep multiplying and additions. And this will end up with something that is still linear. Like something like linear, meaning something like this. A combination of linear functions is always going to be linear. So we use what we call the activation function, which is non-linear, like the sigmoid, like this. When we combine them in our multiplications, etc., we end up with all sorts of functions. So that's why we use the sigmoid functions, or the activation function. Sorry, sigmoid is just one of them. And we have a few. We have a few of them. They can be dangerous for example, the sigmoid is a little bit dangerous with the vanishing gradient, because here, as you can see, we don't have a lot of gradient. It's almost flat here and here. Well, this is the sigmoid. The error function or the loss function will be different, but it will still, we don't have a lot of gradient here. Not a lot of gradient here. We have a lot of gradient in here. So the gradient is very high, and we can follow the slope, how the gradient is going, to find the minimum. Sometimes the minimum is here, or depending on the loss. This is like, that is used a lot, the RULU. Here we don't have a lot of gradient, there is nothing. And here, it's like, it keeps things normal. We are going to visit them in CNNs, where we use a lot of RULU. We don't use sigmoids there. We use RULU for some reasons that we are going to explore. We will explore different types of activation functions depending on different cases later. I just here want to mention them.
What does X represent here? Like
X,
the variable.
X is the output of the neuron. Any output of the neuron is a linear function, and it goes to the activation function.
Okay.
So we have a neuron here. If we take a simple neuron, what it is doing, it's multiplying weights, W's, by X's. And the output will be put into the sigmoid here. Because this is linear, the sigmoid will make it non-linear, something like this, or something like this. And their combination will, the different neurons with the different sigmoid or RULUs will like build any types of functions dependent on the data. Okay.
Yeah, and how do we define, let's say, at the beginning, the weight of the neural network?
That's what we were talking about. The weights in the initialization is used. We use something like this. This is very simple. We have multiple ways that are more efficient. Like we randomly generate them, but within a small interval, like this one.
Okay.
And there are other ways: variance calibration, the batch normalization, etc. We are going to examine them later, how we initialize. And then the gradient descent, with the help of backpropagation, we update these weights to learn based on the loss function. The loss function gives us the error. The gradient, the backpropagation will give us the gradients to tell us how to update the weights, and the gradient descent will do this update and follow the slope. We are going to see it more. We are going to see more of these activation functions later. So now the gradient descent variance. We saw last time some like the regular gradient descent. The regular gradient descent, what it does, we use the whole data set, and we have a data set here. Let's say we have this data set. We have the y here, the x is here, xi, the different inputs. Normally, the regular gradient descent, what we do, we try them all the samples, and we see which one my main network is getting right, which one is right, which one is not right. And the loss function will compute some error based on all these outputs and what the network has found. Are you happy with this, guys, so far? No?
Can you repeat it?
Yeah. The regular gradient descent, what it does, it takes the data set,
okay,
compute the output of the network, what is called y hat. The regular y is the output of the data set, on the data set, the label or the class. Okay? The network compute y hat. We call it y hat, but the network computes from this. The network will take this and compute another y. This is the real y. And this is what the network has found. The error is what is the difference between them.
Yes.
The loss function that we saw last time takes these two and calculates some error based on how many we got right, how many we got wrong, etc. We use, for example, for classification, we use the cross entropy that we saw last time. We saw that formula with logarithms, etc. So we do this. The regular gradient descent will use the whole data set, the entire data set, to compute all the errors. But sometimes the data set will be too big. For example, say billions, 10 terabytes of data. It doesn't fit into memory, or it may take too long to compute the whole thing, the whole error. So in that case, it's better if we don't use the whole data set and we use just a small chunk of it to avoid computing a big loss. The loss function, the big loss will be just the different losses, all the losses. We sum the loss for first example, second example, all of them, all the errors. We do the whole sum. And this can be huge to compute if we have like a 10 terabytes data. So what we do, we use what we call not the gradient descent, the regular gradient descent, we use the stochastic gradient descent. So this is just an example of what is the gradient descent. It's just follow the slope. To go to the bottom, you are going to go this way. You're not going to go this way, to this direction. Even, for example, if you are driving, guys, in a valley or in a city where there is a sea and there is a mountain, like a city that is on a hill, and you are going to the beach or to the port. And you know nothing about the place. What generally do you do? I have seen many people doing it when driving. You follow downwards. You drove down. You drive down to reach the port, because you know that the port is at the bottom. And if you are in a hill, you just look at the road that goes downward. Do you agree with me?
Yes, yeah.
Yeah, it happens
Yes.
to everyone. When you are driving, especially before we use the GPS, when we are driving to a city like Algiers, for example, and we wanted to go to the port, if we didn't know anything about it, we just drove downward. We know that the port should go there. There is no port if we go up a hill. Of course, there is nothing. Otherwise, it's maybe it's not logical to go uphill. We go downwards, and the probability of finding the port is much higher, and it happens most of the time. So this is it. The gradient descent is follow the slope. And the loss function is simply a function of the different weights. This is what defines the terrain. The loss function is our terrain. So the stochastic gradient descent, what it does, simple compared to the gradient descent, instead of using the whole data set, which is expensive, especially with larger data sets, use mini batches, sometimes 32, 64, depending on your case, 128, 256, and compute the gradient only for this small sample that were selected randomly. I should have mentioned it here. They are selected randomly, so like sampled randomly. For example, 256 out of the big data set, and we take them randomly, and we compute the gradient using backpropagation, and we update things. We call this, because it's randomly sampled, we call this the stochastic gradient descent. Stochastic because there is randomness there. So that way, the data will fit in memory, and we can speed up the operation. And especially sometimes a small number can represent quite closely the whole data set. If we sample things randomly, we might represent like the big data set and get a gradient that is very close, or a loss function that is very close in terms of values to the original one. And we can speed up the operation like by a lot. Also, it's not the only problem why we use the stochastic gradient descent. And by the way, stochastic gradient descent, we repeat it. So we take a mini batch, we compute the gradient, we update the weight, and we do it again, because we haven't taken all the data set. We haven't like built my W's around all the data sets. So we do it what we call through multiple iterations. So we take, and in each iteration, we subsample. For example, if we are using 256, in each iteration, we subsample from the original data set 256, and we update the weights. Second iteration, we do the same thing. We resample randomly 256, and we do the same thing again, etc. We keep doing it until the weights are stable, or we have some termination condition. Now, guys, I want you to focus on this. This is a major problem in optimization, and we are going to explore it later more in the next session. So, saddle points. We said that what we want is the minimum. The minimum is characterized by what? How do we know we are in a minimum? The minimum is characterized by
convex.
No, this is convex.
Convex.
But the minimum, what does it have? Well, its gradient is how is its gradient?
Near to zero.
Yeah,
Zero.
Zero gradient, or the derivative is zero across all directions for all variables. However, this point in here, its gradient is what? What's the value of its gradient here, of this point?
0.
Yeah, it's 0. It's not a minimum. Is it? Is it a minimum or not?
No, it's not.
It's
not a
not
minimum.
minimum. There is a
But
point
the gradient is 0. There is a real
close
problem
to
here.
it.
Serious problem. If the gradient descent comes here, it will be stuck. Because it finds that the gradient is 0, there is no point of trying something else. So we call this
Local.
It's not even a local minimum, because there is a point next to it, for example, this point, just next to it, and it is better. It's not even a local minimum. There is a point just next to it, and it is better than this point.
So we should not use the gradient to figure out
Well,
about.
we can still use the gradient descent, but not the regular one. This is called, remember it, the saddle point. Saddle is what we use to ride a horse, because it looks like this thing that you put on the back of the horse to ride it. And it has its like a similar shape, the saddle point. Saddle point. So what shall we do? Same goes here. Here we have a lot of saddle points. Many, multiple, flat surface, that are like represent a multiple saddle points. And it is not a minimum. Like there is like next to them something that is minimal. What's the problem, guys, with this? This is a more serious problem than this one, if you want to avoid it, because it's flat surface. So in large networks also, differences between local minima. So we can, for example, we have here it's a local minimum, a local one, a local one. This is the global one. This is the best solution, but of course, gradient descent can't find it if we start here. If we start here, it can't find it. But if we start here, it will not. It will go here and stop here. However, some phenomenon that has surprised till this day many experts, that is happening in real life, in complex problems with large neurons, with a large number of neurons. The difference between local minima is very small. It means that when we have a large problem, this is just a simplification, because we are in multiple dimensions. It's just in 3D. In multiple dimensions, we can't represent it. But in real life problems, but with a lot of neurons, which means local minima are like that. The difference between them is very small. Which means they provide a comparable solution in terms of quality. This is a phenomenon that is happening in real life, like a really impressive phenomenon. We don't know why, but it happens that this is the case. In real life, local minima are very close to each other and very close to the global one. This is the global minimum. Local ones are very close to it. And most bad minima, the bad ones, are actually saddle points. This is what is characterized in real life. Impressive, really impressive. It's like real life is made for neural networks, but with a better version of the gradient descent, the version that can escape saddle points. And it happens that if you have a look at the saddle points, what is weird about it? If we like nudge it just a little bit, we can fall from it. If we go slightly here or slightly here, we can escape it. Just a little bit. Do you agree, guys? No?
Can you repeat, please?
Sure. So, do you understand how what I explained about real life with large neural networks?
Yes.
That local minima are very close to, in terms of quality, to each other, and close in terms of quality to the global ones. Which means we find any minimum, we are fine with it. And most bad minima, most bad ones are actually saddle points, like this one. We have here a local minimum here, a local minimum here. Yes or no? They could be global ones, both global, and they are equivalent in terms of quality. We have a local one here and local one here. This is a bad one. Yes or no?
Yes.
They are very close to each other. Real life is like that. With complex neurons, neural networks, most real minima are close in terms of quality to each other, like this one. The bad minima are actually saddle points. So we just need to find a way to escape saddle points. If we can escape saddle points, it seems that we can solve almost every problem with deep learning, almost. Because most of the complex problems have like this, share this configuration. This is a heuristic with like multiple researchers trying to find these things. So we just need to find a way to escape saddle points. And as you can see here, this saddle points is highly unstable. If we move just a little bit here or a little bit here, we can fall. We can find another slope. Do you see it, Yusuf?
No, I missed this part.
If this is the saddle point.
Yes.
If we, for example, we are starting here, we follow the slope, so we go to the saddle point. But if when we reach it, if we move slightly, just slightly, for example, here or here, the slope has changed. Now it's this way.
Yes, it goes down. Yes.
It goes down. So the saddle point is, if you look at it, it's highly unstable. We just nudge the thing a little bit.
Okay. Yes.
And it can fall. It can follow the other slope, the real slope.
So what you need then to shift? Yeah.
It will shift a little bit. We just need something, some vibration to give it, to make it go this way. If we start here, that's fine. We are going this way, and we end up here. But if we start here, we can end up here. If it is the real gradient descent, the perfect one, we will reach this point. But if we add some noise, for example, to it, we can end up here. So you can see that saddle points are highly unstable. There is always something next to them that can make them like offer a better slope next to them. And this is one way of escaping the saddle points. Are you happy with this explanation, Yusuf?
Yes.
Well,
yeah.
all of you guys, of course. Are you happy?
Yes.
Perfect. Please tell me, don't be shy or anything. It's not trivial topics. Believe me, it's not trivial at all. I have seen like people with high degrees and struggling with this, so don't be shy. So this is sayings from like experts and researchers from neural networks. So this is in a book or a paper. An MLP multi-layer perceptron with a single hidden layer has only saddle points and no local minima. Well, this is his opinion, the opinion of these authors. They say that most of the time it's saddle points when we have an MLP with a single layer, just one single layer, and one global minimum. When we say there is no local minima, it means there is one global minimum. This is a powerful statement. It means that if we have like a neural network, an MLP, with one single layer, which means this, something like this. These are the inputs, these are the hidden layer, and these are the outputs. So this is a rather small neural network, etc. We have this, etc. They say that it has only saddle points and one global minimum. It said there is no local minima, which means one global minimum. Which means that if we can escape the saddle points, it's almost like we have a complex problem. Do you agree with this? If we can escape the saddle points, the problem becomes convex, which is a very strong assertion. Well, this is their opinion. I haven't read like if there is a proof about this, but this is a powerful statement. It's like we are in a complex problem, and we still can end up with a convex solution. Another authors, they say an exponential number of saddle points. There is an exponential number of saddle points in large neural networks. There is a lot of them, and not that many minima, real minima. Okay, guys, are you happy?
Yes, yeah.
Perfect. One problem is that gradient descent algorithms, they like saddle points. But saddle points are highly unstable, surrounded by better or worse values. So a small error can make you escape them. One way of escaping saddle points is we can add small perturbations to the gradient. We don't follow the real gradient, like this, but we add some perturbations so we can not go into this direction, but for example, this direction. Slightly moving, and we can like escape it. Also, the stochastic gradient descent, because it's not computing the full gradient, the full error, the full loss, it's computing just a small portion. So the gradient will be slightly different with the stochastic gradient because it's not using the whole data set, it's using just a small portion. So the gradient that you are going to compute based on the stochastic is going to be slightly different than the real gradient that is going to be used for the whole data set. So it adds some differences. This way, we can escape saddle points, but there are more sophisticated ways of doing it. For example, this one. These are different variants of the stochastic gradient descent. So we have here the normal SGD, momentum. We are going to explore them next time, plus other things, and more like sophisticated algorithms. You can see here the red one and the green one, sorry, just the red one. The SGD is stuck. Others takes time to escape, like momentum and NAD. It takes time to escape, and the three others are escaping very fast, especially this one. It doesn't mean it's always the best, but RMS prop is used more, plus Adam that we are going to explore next time. But you can see that these guys quickly escape the saddle points because of their properties. You can see them. But these ones couldn't, especially the regular gradient descent, the stochastic gradient descent, because its loss function is very close to the real loss function. It couldn't escape it. Others, these two guys, spent some time to go, but they still made it to the minimum, to the global minimum or the local minimum, real local minimum. Okay, guys, any questions so far? No question? I think we are done for today. That was I'm happy with this session. You seem to have grasped many concepts. So we stop for today and we continue next time with what we are going to do next about the theories on neural networks and deep learning. After it, we will start with probably not next time, but after it, we will start with CNNs and computer vision, where we'll have more practice. So thank you, guys.
Thank you, Rida.